This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Keeping your teams on top of the latest tech developments is a monumental challenge. Helping them get answers to urgent problems they face daily is even harder. That's why 66% of all Fortune 100 companies count on O'Reilly Online Learning. At O'Reilly, your teams will get live courses, tons of resources, interactive scenarios and sandboxes, and fast answers to their pressing questions. See what O'Reilly Online Learning can do for your teams. Visit O'Reilly.com for a demo.
Welcome to Software Engineering Radio. I'm Akshay Manchale, and today I'll be talking to Tomer Shiran. Tomer is the Chief Product Officer and co-founder of Dremio. Previously, Tomer led the product management team at MapR, where he was responsible for product strategy, roadmap, and requirements. Prior to MapR, Tomer held numerous product management and engineering roles at IBM and Microsoft. Tomer, welcome to the show.
Thanks for having me here.
Awesome. So before getting into data lakes, let's talk a little bit about the history and how we got here. Everyone is familiar with databases, and they've existed for many decades. But at some point, there was a transition and evolution to having data warehouses in an organization. So can you talk about what were the motivations and what led to that need to have a data warehouse?
Sure. Yeah. Back in the day, it all started with people having databases where they were running their applications or storing the data for their applications and performing transactions there. And there was a need to analyze that data. And for a couple of reasons, sometimes it became hard to analyze the data on that operational database for reasons of, first of all, you didn't want to impact the performance of the application that was running, and that was potentially a mission critical kind of OLTP application. And then also in some cases, you wanted to kind of centralize data from multiple places, multiple sources, or multiple databases, and be able to analyze data that's coming from many sources. And so being able to move that data into one place, and ultimately that became the data warehouse. And I think in many cases, the data warehouse technologically was just a database. It was the same type of technology that people were using for their OLTP databases, whether that's an Oracle database or something else, SQL Server and so forth. So that was kind of the rise of the data warehouse.
Yeah, and from data warehouses and more recently, we've had a transition to having data stored in different forms. You had structured data for the most part, and then you have unstructured NoSQL-like databases that started coming about. So what was really the motivation there, and how does that contrast with respect to the data warehouse evolution before that?
Well, I think there's two aspects here. The NoSQL database movement and technologies like MongoDB and Elasticsearch, which you could kind of put in that bucket, were all around making the developer more productive. So a lot of applications were being built with JSON and nested structures, and it was easier to represent kind of objects in the real world using those structures as opposed to kind of flattened out tables. And so that's the reason people started building, or companies came up with these NoSQL databases like MongoDB, which were much nicer, I think, for a developer to go build an application. And then in parallel, I think there were also, for analytical workloads, a lot of data sources that were, maybe log files and other data that wasn't necessarily your traditional kind of star schema, right? Very structured, data that people were putting in data warehouses and databases. And so, I think that was another kind of thing that drove the rise of these semi-structured data sets.
Right. So agility, I guess, developer agility was like a huge portion for that change. Coming from there, what led to the emergence of, say, data lakes and looking at your data as a data lake?
I think the early days of the data lake were all about the ability to kind of store larger volumes of data and ingest larger volumes of data more easily into a centralized kind of repository. Right. If you think about the data warehouse, a ton of effort goes into, creating those models, creating the tables, the schemas, making sure that the data that's being ingested, meets those, having to change the schema before you actually ingest any data. So pretty rigid and takes a lot of effort. And so once systems like Hadoop back in the day, this is like 2009, 2010, once those were created, the ability to just have a repository where you can dump files, whether they're log files or more structured data, into a single system and pay a very low cost per terabyte or gigabyte, that was, I think, a big motivation there. I think what then happened, early on in the world of data lakes, a lot of the processing was this kind of batch processing, right? It was really designed for these MapReduce jobs originally. This is pre-Spark and pre kind of being able to run SQL on data lakes. But one of the really interesting things that kind of came out of this is the creation of many different types of computational engines, right? So the ability to use one engine for a developer that wants to do kind of batch processing, right? Something like Spark, and a different engine for somebody for kind of workloads that are more like interactive SQL and BI, right? That's what we do at Dremio. So all sorts of different engines, different machine learning engines that all interact with that same data. That I think has become the defining feature of the data lake, which is something you just can't get in a data warehouse.
Right. I guess the separation of the compute and storage aspects of it really led to the emergence of various compute aspects. But on the storage side, is it still Hadoop and HDFS, or how do people look at a data lake? Is there a classic data lake product, so to speak?
I think now for us, what we see is the vast majority of data lake projects are actually in the cloud. And so once companies started moving to the cloud and things like AWS and Azure, right, where you have these storage services like S3, which is infinitely scalable and very inexpensive, it's $20 per terabyte or less, and you don't have to manage much. You only pay for what you use. It's just, and it's available geographically in many different regions around the world. So you have a much better solution now for the storage of a data lake in the cloud. And you have the same thing in the other cloud providers, for example, ADLS on Azure. So that's created really a much more powerful concept. And, this is now being taken advantage of by both cloud data warehouses and cloud data lakes. So the cloud data warehouses take advantage of the fact that you have this separate kind of infinitely scalable storage system, but they separate the compute from the storage. But the data itself is still stored in a proprietary format that is, tied to that one data warehouse and can't be accessed by other computational engines. You have to pay that data warehouse vendor to get the data in, to get it out, to anytime you want to do something with it. Whereas with cloud data lakes, what happens is that the data inside of these storage systems like S3 is stored in open formats, right? Open source formats like Parquet is a columnar format that's high performance, and increasingly also open table formats like things like Apache Iceberg and Delta Lake. And by having the data stored in open formats that can be accessed and transacted on from different systems, right? Dremio being one of these systems, but you can use other engines that are out there. You can use Spark, you can use Databricks, you can use Presto, Athena. There's a lot of different engines and tools that can interact with this same data. And so you're not locked into one specific data warehouse vendor.
Is there a particular defining characteristic that you see for a data lake? Is it the variety of data? Is it the volume of data? Is there a single defining characteristic that you normally see?
Well, I think data lakes typically are used in situations where companies have relatively large volume of data. So you typically see this being used by either enterprises, so larger companies, they typically have a lot of data, or you often see this even with smaller companies that are tech companies, so venture-backed technology companies where they may be a small company of maybe a couple hundred people, but they're serving millions of users, right? Because that's just the nature of their business, and so they're generating a lot of data and have the need to analyze a lot of data as a result of that. So that's, I would say, typically the defining kind of element of a data lake. Historically, there's been talk about, back in the days of Hadoop, people talked about, well, you should use a data lake if you have unstructured data, semi-structured data, things like that. I think these days, most of the data that people use is structured data. So it's not like, okay, people that have structured data are putting that in a database and people that have unstructured use a data lake. It's actually the vast majority of use cases where we see people using data lakes. The data is structured. It's in tables that have, rows and columns and schemas and, and they're doing processing on that data. So that's really no longer a big distinction, I think.
So before you actually have data stored in, say, S3 or something, you may have data in different databases. Maybe it's in a data warehouse. What's really the ingestion path into, say, S3? What sort of ETL tools do people normally use to get their data in?
So I think you can look at the data that's out there and kind of think of it as two different categories. One is data that's being generated in, say, operational databases. These are the the OLTP relational databases, Oracle SQL Server, and it's the NoSQL databases like MongoDB. And that data needs to be ingested into S3. And then you have, especially for companies that were born in the cloud or new applications that are being built in the cloud, a lot of the data exhaust from those systems kind of natively just lands in, starts its life in S3. Fortunately, what's happened is, and this is thanks to the value proposition, the benefits of systems like S3 that are so inexpensive and infinitely scalable, they've become the de facto system of record in the cloud, right? This is where everybody puts their data. Even, you look at companies that use data warehouses in the cloud, the vast majority of them, probably over 90%, the data is actually first being moved into S3 and then from there loaded into a data warehouse. And that's because it's so inexpensive and so easy to put the data into S3. I'd say a lot of companies, it's very simple to kind of upload data into S3, so they just kind of do it themselves. They write some code from in Python, use some Amazon tools. Others use ETL tools to do that. So every ETL tool basically now supports getting data into S3, whether it's the more traditional ETL tools, Informatica, Talend, some of these newer data pipeline tools, Fivetran, Matillion, and Stitch, etc. So there's a lot of different options for people to get data into S3 these days.
Well, S3 itself is kind of like an object store, right? So how do you catalog and organize your data? If you have a database, it's fairly straightforward. You have a schema that defines like what sort of tables you have, and then you have the actual columns within it also well defined. Whereas in S3, you're just talking about a single file, right? So what's the cataloging and organization there?
Sure. So you're right. S3 is at its core, it's an object or a file store, right? So you're storing files, and so there's really two ways to kind of define. Maybe let's call it three ways to define a table in this kind of a system. So the most simple, but maybe least flexible way is you store the files in kind of a self-describing format, right? So you just drop a bunch of files in a directory. All these files are in a format like Parquet, Apache Parquet, or maybe even just JSON files. And because those are structured, many engines, like Dremio can just, point at that, read that, query that, right? And if you structure it well, you can also even support partitions, right? By having kind of nested directory path. So that's one way. The second generation that was created kind of on top of that is systems like Hive Metastore and Amazon's Glue catalog. So these systems provide kind of a metadata layer or kind of a description layer on top of those files, right? So now you have, rather than just pointing at a specific path and that's your table, this Metastore or catalog, Hive Metastore or Glue, they basically store the definitions of all these tables. And for each table, they store the schema, and they also store kind of the list of files that make up that table. So it's kind of a separate system. And that's great. It adds a lot of structure. It makes it easier to have kind of consistent definition of tables across different systems. One of the challenges there was just the scalability of those systems, and also the fact that they're kind of disconnected from the data itself. So you have kind of the files being stored on S3, but you have the data being, or the metadata being stored in a separate system that is transactional. And so it's hard to kind of do anything kind of transactional that way. And so what you've seen in the last year is the rise of these table formats, native table formats that are transactional and support data mutations and support time travel directly on systems like S3. And so you have two main kind of competing technologies there. You have one project is called Delta Lake. It was created by Databricks and primarily supported by their system, although that data can be queried from other systems like Dremio and others. And then I think more relevant is Apache Iceberg, which is a project created by Netflix and now backed by Apple and Airbnb and Stripe and Adobe and Alibaba, and basically many of the largest tech companies are now behind Apache Iceberg. And the idea there is to have an open source table format that supports transactions, supports record updates and deletions, supports time travel, and allows these types of transactions to happen from basically any engine, whether it's Dremio or Spark or any other engine out there. They can all perform transactions and updates on the data and do that in a consistent way without kind of harming each other.
So Iceberg sort of uses S3 as a backing storage system through which you can push data in. Is that right?
Yeah. So Iceberg, you can think of Iceberg as basically it has manifest files, basically files that describe the data that are stored alongside the data. So in S3, you have a file that basically points to what are the data files and also includes information about the schema. And it does it in a way that when an update is made, it doesn't lose the previous version. It kind of it keeps track of the deltas. So there's a new manifest file And then kind of the root pointer points to the new manifest file, and that allows different engines to support transactions and version control on this data.
Interesting. So I want to dig into some of the storage formats a little more. We started with, say, XML, and JSON was super popular early on in the decade due to the whole NoSQL storage systems. Now you have Parquet, Avro, a couple of these formats. So can you walk us through some of those newer emerging formats and what they're really used for?
Yeah, I think if you want to call XML and then JSON as kind of that first generation, I think the focus there was on interoperability, on having a standard that different systems can talk to, right? And of course, JSON being a much simpler, much more elegant, I think, than XML. And back in the day, I was when I was starting my career as an engineer at IBM, I was totally immersed in this world of XML. I was using these XML spy tools, and I could create XSDs, while I was asleep. So that was the standard back then, and that's improved. But when you think about analytics, it's not just about storing the data in a way that's interoperable and can be understood by different technologies. It's also about performance, right? You can't just you can't store it in kind of a text format like JSON or XML, because that's not going to be very efficient for querying. And so then you saw the rise of these newer formats, and Avro and Parquet are examples of that. ORC is another example. And there, kind of the world separates into two different formats. There's the row-based or row-oriented formats where, kind of from a binary standpoint, each record is stored, the first record is stored before the second record, which is stored before the third record. So you have all the data for that first row before all the data of the second row, and so forth. And then you have the columnar formats where the data is structured in a column by column. So, maybe take the first, 1,000 records of the data set and store the name column for each of those 1,000 records, followed by the ages of all the 1,000 records, followed by the address of those 1,000 records. And so that's what's called the columnar format. So Parquet is a columnar format, and that has a lot of advantages in terms of things like compression. For example, you can be much more efficient in terms of how well you can compress the data if you're storing, for example, all the dates, right, one after the other, right? You can use things like delta encoding and so forth. And then it also has another benefit when you're using a columnar format, in that when you think about query processing, we once did a study of some of the largest Dremio customers, some of the largest banks in the world and tech companies. And what we saw is that on average, 5% of the columns of a given data set are actually being queried, right, on a regular basis. So you have these data sets that have 1,000 columns in them or 500 columns in them. And out of those 500 columns, maybe 20 of them or 25 of them are actually being queried, right, by the users. The rest are, they're stored there for reasons of wanting to maintain that data, but nobody's accessing them. So if you think about doing query processing, the ability to only read from disk or only read from S3 the data that's applicable to that query can save you a lot of time, right, in terms of how fast you can actually process that data and run the query.
So let's say you're a business with a standard traditional database, right? And you want to push that data into your S3 like data lake storage system. How do you manage ingestion in terms of data quality? You could have multiple databases within the organization. So data quality is really important with respect to how you're pushing that data into your data lake, right? So what's the admission control look like?
There's not one magic solution or ingredient to achieving data quality or ensuring data quality, because at the end of the day, it's a business problem, right? It's something that's a custom problem to your situation as a company, right? And the cleanliness, how clean the data sets are. And the same problem, it's no different really if you think about it from data lakes, data warehouses. You have the same challenges regardless, right? But one big trend I think that has happened in the last few years is a shift from what was called ETL, or extract, transform, and load, which was how you kind of got data into like data warehouses, to now everybody's doing ELT, which is extract, load, and transform, right? So the order changed. The transform, the T went from being the middle to being the end. And the reason for that, if you think about it, that when it was ETL, what was happening is that you had these tools like, say, Informatica or even just scripts that were actually doing this transformation as the data was being moved from the source system into like the data warehouse or the data lake. And that has all sorts of challenges, right? First of all, the fact that these ETL tools, they can't scale anywhere near the same level as your data warehouses or your data lakes, right? So as soon as data volumes got big, that typically didn't work. Also, being able to kind of reproduce or go back to that raw data and being able to change the transformation or figure out what went wrong becomes harder. And so, for most companies now, the standard is ELT for any new kind of use case. And so what you do there is you take the data from the source system, you pretty much dump it into something like S3. And the great thing is because also S3 and ADLS and all these kind of cloud storage systems are so inexpensive and so easy, you don't have to worry as much about the cost, right? When you're paying that little. So you're not worried about that. You put the raw data that you took from the source system, you put it inside of S3, and then you do that transformation, and then you clean the data. So you don't necessarily give everybody access to that raw dump of your database. You do some transformations, you clean the data, maybe you apply some security policies, and then you expose that to kind of the users.
Right. So since you are saying the transformation is actually going to happen towards the end, I assume that transactional nature of data is not directly visible when you're loading data into a data lake. It's just you dump it there and then later you figure out what has happened. Is that typically how you go about transactional data?
Well, I think what you're hitting on is like data freshness, right? Like how fresh can the data be? So if I'm taking data from a source system, putting it in a data lake, well, no matter what, there's going to be some latency, right? When I take data from one place and put it in another place for it to be queried. But you do want to shrink that latency as much as possible. And so there's newer approaches that a lot of companies are using now, and also data kind of pipeline technologies, things like Kafka, where for use cases that require kind of more real-time data, a lot of times they're being ingested that way as opposed to kind of a batch process from like a database into just kind of batch jobs, taking chunks of data and putting them into the data lake, right? So it really depends on the need there. What we've found though is that I'd say the majority of use cases, it's less about having the last 1 minute or last 5 minutes of the data available for queries, especially if it's a human kind of use case where somebody's going to actually look at the data for ad hoc analysis or kind of maybe a business intelligence dashboard. What's more important is that it's not taking you weeks or months, right, to get this to work and for any change to happen in the system, right? That's probably the bigger problem than, okay, if everything were working and the only problem was I can't see the last 5 minutes of data. For most use cases, that's okay. Not always, obviously. If you're trying to do fraud analysis or fraud detection, you may need obviously the live kind of real time data feed.
Right. This is great for analytics. One thing is now that you're actually moving a lot of data from different sources into a data lake, what is compliance like? You might have GDPR requests that say, I want all of my data deleted. Now you have it in various forms in various places. So how do you conform to some of those policies?
At O'Reilly, we know your tech teams need quick answers to their most urgent questions. They need to stay on top of new tech developments. They need a safe place to learn the technologies your company adopts. And they need it all 24/7. Well, they can get it all at O'Reilly.com. With O'Reilly Online Learning, your team gets live online courses, tons of resources, safe interactive scenarios and sandboxes, and fast answers to their most pressing questions. Visit O'Reilly.com and request a demo.
From my perspective, a key to having data governance and security is to minimize the amount of data copying that's happening. So if you think about the traditional architecture, even in the cloud, is companies, they have their data either being generated directly on S3 or they're moving data into S3. Then they take a subset of that data, they load it into a data warehouse for querying. Then within the data warehouse, they create copies of that data because different users and groups have different needs around how to view the data and also for performance reasons, right? The raw data is too big in the data warehouse, so the queries are slow. And so then you want to maybe summarize, pre-aggregate or summarize it and create kind of more filtered or aggregated views or tables of that data. And then the access often is too slow. And so then additional copies get created by kind of creating, BI exports. If you're using tools like Tableau or Microsoft Power BI, you're creating what's called exports or imports into the BI tool. And if you're a data scientist, you're exporting data from the warehouse into like a local file on your laptop so you can do data science. And so you can see in this whole pipeline, there's so many copies of data. And that makes it very hard indeed to deal with things like GDPR because somebody submits a request under the right to be forgotten, right? They say, I want you to delete all the records related to that person. Well, if that data has been copied all over the place by different users, it becomes basically impossible to really satisfy that. In many ways, the centralized kind of data team doesn't even know where the data is anymore. So that's been one of our focuses at Dremio. We call it the no copy architecture, is to really minimize the need for data copies, right? You want to have one centralized system that can support data democratization and give people the performance that they need, all the way from, of course, the kind of the ad hoc, experimental data exploration kind of use cases, but all the way to that sub-second kind of BI workloads that in the past you'd had to go through all that complexity to achieve these kind of BI performance requirements.
Yeah, I want to come back into Dremio and how you're doing the zero copy analytics. But before we get there, can you talk through some of the common use cases for a data lake that you see in the industry today?
Sure. I think the data lakes are used horizontally in really every industry, right? So when I think about the companies that we deal with in the world of data lakes, it's everything from the world's largest banks to the largest insurance companies to tech startups. It's really all over the place in terms of the kind of the industries and what they're doing with the data. But the common thing there is that the companies have a lot of data and they're trying to get value out of that data, right? They're trying to process that data. They're trying to query that data and present it in dashboards. They're trying to do machine learning on that data. So they have a variety of different workloads that they want to bring to that same data. Right, and that's one of the advantages of the data lake is that that same set of data, and this is why it's so beneficial to have this architecture where you have kind of the data stored in open formats. The same set of data can be processed by all these different engines for different use cases. So to give you an example, one of our customers is a tech company, and they're optimizing their supply chain, right? So they have a lot of data from all parts of the kind of the supply chain, and they need to be able to visualize this and present this to all the way from the folks that are responsible for understanding what's happening in the supply chain and where are the bottlenecks, all the way to the executives that are looking for kind of bigger picture, how are we doing, how many units have we moved, and so forth. And being able to do that requires you to be able to aggregate the data and provide that big picture view of it very, very quickly, because that executive that wants to log in and look at a dashboard, they need a response with less than a second. And it also requires the ability to drill down into the detail level data, right? So down to the individual records and what happened to this, what happened to this box and so forth, right? So it goes all the way down to that. But yeah, in many cases, we're talking about a variety of different use cases, all kind of being executed on that same data.
There's a lot of value to be extracted, and you could be in an organization that is having a lot of data from various sources inside of your data lake. And how do you go about exploring what's actually available? Is there any exploratory tools to kind of discover the kinds of data that you have that might lead to richer analytics?
Yeah, there actually are, and in fact, there are vendors that this is what they do. They've developed these data catalogs, right? So you have companies like Calibra and Elation and others that this is exactly what they do. They try to kind of surface the meta information, right? The descriptions of the data sets. They provide maybe a search bar that allows you to search for, if you know kind of what you're looking for. Hey, I'm looking for sales data. I'm looking for things like that. Then you put it in the search bar, and it will surface tables that maybe have that column, or the columns can be described, and also you can have tags on these different things. So it gives you a level of kind of data management and kind of a catalog that you can explore what you have. And then I think for most companies, it comes down to a wiki, to be honest. I think at the end of the day, there's a lot of tribal knowledge. This is a problem that has never been truly solved to the end. And I think there's a lot of tribal knowledge and a lot that you can learn from other people within the organization. And you see a lot of that obviously happening as well, because there's descriptions of data, but they get out of date. And as the data is changing, and you don't really understand maybe what exactly is stored in that table. So this is where it's important for the company to have kind of really good data management kind of processes as well. It's not just the tools.
Okay. Now I want to switch gears a little bit and talk about Dremio, which is obviously the company that you've started. So what is Dremio, and how does that fit into the ecosystem?
Yeah, sure. So we describe Dremio as a data lake service, or a next generation data lake service. And the idea really is to bring kind of the capabilities that you would traditionally have in a data warehouse, to bring that directly to the data lake and allow people to run SQL queries directly on their data in systems like S3 and ADLS. And so really what we do is we help companies take advantage of all that data they have in their data lake, not just for kind of the data scientists that are doing ad hoc and kind of exploratory work, but for the full spectrum of use cases that you can accomplish with SQL. So we're the SQL engine for the data lake. And that ranges from people that are using Power BI and Tableau, and they want that sub-second response time on their dashboards, all the way to people that are doing ad hoc queries and kind of running one query at a time, and for many minutes, and kind of exploring the results of those queries. So we're the SQL layer for many of the world's largest data lakes, the largest, many of the largest banks in the country, and largest tech companies, retailers, insurance companies. So it really spans every vertical.
So something that I read on when I was going through some of the docs was about virtual data sets that you can create. Can you tell us more about what virtual data sets are?
Sure. So you could think of the value proposition of Dremio as having more than two, but let's talk about two key kind of components. One is that performance element, the fact that we can run queries and achieve the performance that typically you couldn't get on a data lake historically. And then the second thing is what we call a semantic layer. And so the idea here is that in a company that has lots of users that want to consume data, and increasingly that's really every company, because everybody wants to democratize data and put it in the hands of the business. You want to be able to make the data accessible and consumable and secure, right? And you don't want to create lots of different copies for every single user in the company, right? So we have these virtual data sets where you can very easily create kind of different views of the data. Whether it's could be as simple as renaming a column of a data set, all the way to masking a specific column for PI that has PII information, or cleaning the data or joining it with something else. But you create these virtual data sets, and that becomes kind of that semantic layer. And then regardless of what tool you're using to access the data, if it's Tableau or Power BI, or it's a Jupyter Notebook, if you're a Python user, you're basically seeing the same definitions, the same virtual data sets, regardless of how you're accessing that data. And that makes it very, very easy for like the data team, the data engineers, to provision data sets for different users, right? They don't have to go and create a separate copy, because creating the copy is easy. It's keeping it in sync later is the hard thing, right? As data is constantly coming in 24/7, once you start creating copies, you have to keep those data pipelines going and make sure you have many nines of availability on them, and so forth. It becomes very difficult. So we create these virtual data sets, and just creating virtual data sets alone is not enough, because sure, you can create views in a database, but then you query them and it's really slow, right? Because a lot of compute is happening kind of on the fly. And so we kind of complement that with something we call data reflections, which is a way in which we materialize different views of the data. So you can imagine a data set that maybe has billions or hundreds of billions of records, and you want to have different views of that data. Some are maybe aggregated already, maybe sorted in different ways, but you don't want the users to have to know and guess which version of the data they should use. Should they use a pre-aggregated version because they only need aggregate level data? Should they use this sorted version because they're doing a filter on a specific column, right? The users of the data, the consumers of the data, they're never going to understand things at that level, right? They, as we talked about earlier, just knowing which data sets you have in the company, that alone is hard enough. So let alone, if you had like 50 different representations of that data set. So what we do at Dremio is we take these, the users, they operate in the logical world. They think about kind of the data sets and the virtual data sets. And then our query optimizer basically gets the query, compiles it into a query plan, and basically rewrites that query plan internally to leverage these different data reflections automatically and transparently to the user. And so you get that performance that you could get from highly optimized data structures without having to understand any of that.
When you say data reflections, is that something that's actually materialized? Is that just a virtual representation of sorts?
So you have two different things. You have the virtual data sets, and those are kind of like views in a database. But we provide a much nicer interface for people to kind of view them and interact with them. And then you have the data reflections, which are various materializations. And so you could think of a reflection as kind of being like an index in a database, right? An index, say if you went to an Oracle database or a Postgres database, and you create a table and you create an index on it. The index is a different data structure, right? Maybe it's a B tree that has that column, kind of a copy of that column, but sorted in a specific way and kind of with pointers to the different records, right? So an index is an example of a materialization. A cube in OLAP is an example of another kind of materialization, right? So there's different kinds of materializations that you can have, and they're all good for different workloads. But the idea is that if you can take that complexity away from the users and you can automatically take advantage of the existing materializations when somebody runs a query, well, then you can make that a reality, really, right? It's not, you don't have all these problems that you had back in the day with all these OLAP cubes that people would have to build, and then the users would have to point their BI tool at that cube, and the user wanted something that wasn't in the cube, and it took 2 months for the IT team to refresh that cube, and all those problems basically go away.
So it's kind of like a self-service way of getting to what you want. And on the compute side of things, like what other common tools or common processes exist? You have your data lake, you have data coming in from various sources that you're storing. How else is it used? What sort of tools are used for what kind of applications?
When you say tools, do you mean in the data lake itself?
Yeah, things that make use of the data in a data lake.
Yeah. So most of the time, if you look at the companies that are using Dremio, they're not using Dremio alone, right? Part of the value of the data lake is that ability to use different compute engines, different tools on the same data, right? The data stored in open source formats, and you can use different tools on that. And in fact, Werner Vogels from Amazon, the CTO of Amazon, wrote a nice blog post about kind of why Amazon is standardized internally on data lakes, and talks about the fact that you have this flexibility, but also that you have the flexibility for the future, right? Because as we know, things evolve fast. There's new open source projects, there's new technologies that come up, and this allows you to tomorrow use a new type of engine on that data, right? Without having to do some kind of migration of your data. But today you have systems like Spark that people use on the data when it's more about batch processing and machine learning. You have dedicated kind of machine learning libraries like Dask. You have things like Flink for kind of stream processing. You have Kafka more for kind of on the ingestion pipeline. So there's actually a large variety of tools that people use as well. You have, for example, there's other SQL engines, Dremio, which is obviously the company that I founded five years ago, but you have other SQL engines. You have Hive, you have Presto that some companies use. There's Amazon has a kind of a serverless version of Presto, but those are more kind of, I'd say, for the ad hoc and kind of exploratory use cases only, right? They can't provide the performance that you would need for kind of lower latency workloads and things like BI as well.
What about security? You have different kinds of data now, and how do these compute engines respect the access control or other security-related aspects of your underlying data?
This is where it helps to have kind of a metastore or a catalog for the data, which is respected by the different engines, right? So you have things like Hive Metastore and kind of Glue catalog that can provide permissions. And then actually there's an open source project that we've recently created called Project Nessie, which you can think of it as a next generation metastore for data lakes, which not just provides kind of the schemas and the permissions, but also provides a Git-like experience for the data, where you can have version control and branching and cross-table transactions. And it really makes your data lake look like it's a Git repository. And so all of these types of metastores that are accessible by different engines, for the most part, they're all open source. You can define the permissions in these systems, right? And also integrate with your existing identity provider for the user identities, right? Whether it's Azure Active Directory or Okta or something like that.
So you described the metastore aspect of it, right? So one of the things that I'm wondering is that you have data that's coming in from various sources in different formats. Now, is enforcing some sort of like a meta schema an anti-pattern with respect to data lakes, because you want this variety to be present, but you also want it to be present in a way that's consumable?
So at the end of the day, the fundamental building block for a data lake, for any system really, for analytics, is a table, right? And so that's the level where you want to define the permissions, right? You want to say, well, this table, or perhaps these columns are accessible to these users, and this table or these columns aren't accessible to those users. And so I think that's really important, right? Especially these days where security is such an important thing for companies, especially when it comes to sensitive data and PII, that you really have to have that, right? And data lakes maybe in their kind of, I think early days, 10 years ago, there were questions, is this secure enough and so forth. But, these days, all the Fortune 500, everybody's running data lakes, in many cases in the cloud. So all these problems have been solved.
So one of the things that I've seen about data lakes is people refer to a data swamp of sorts, like, your data lake turns into a data swamp. So how do you prevent that? Well, first of all, what's a data swamp? What point do you call that a data swamp, and how do you prevent that?
I think this is a problem that you have with data lakes and data warehouses, actually, right? Because at the end of the day, if you don't manage what's in that environment, then people start creating all sorts of kind of derived data sets. They don't keep them up to date. Nobody knows what those data sets are. And that's what I think people refer to when they say kind of data swamp, right? It also sounds nice, right? A lake in a swamp. I think that's it's fun to say that. But fundamentally, I think that you have this problem regardless of what system you're going to use. This is where I think we go back to that idea that if you can reduce the number of copies in the system, right? For example, with that semantic layer that we have with virtual data sets and reflections, by not requiring you to create a different copy for every user that needs something a little bit different, and not requiring you to export data from your lake into the warehouse and into BI extracts and so forth. If you don't have to create all these copies, then you're going to have less of that problem, right? You're going to have an organized repository of data sets really that is up to date and well documented, and people can access and get value of.
I want to talk about the operational aspects. How do you see organizations running operations around data lakes? You would have, say, DBAs managing your database clusters maybe, and you have another set of operational engineers who are managing your analytics side of things, right? So how is the operational transformation happening at companies in order to manage their data as a data lake?
I think there's typically, a data team in most companies that's responsible for the data lake. Often it's the same team that's responsible for the data warehouses the company has. So, by and large, they're the ones doing that. What is happening, I think, is that, and this is especially driven by kind of the rise of the public cloud and the ease of use that now comes with, systems like Dremio and other SaaS services in this space, is just becoming easier and easier to utilize these different services on the data, right? So you don't have that same complexity that you used to have with big monolithic Hadoop clusters where you have 30 different open source projects running on the same set of hardware, and you're constantly having to tweak and deal with memory settings and upgrades of different software components and keeping them kind of compatible with each other. Those types of problems go away when you're running in the public cloud, because you have this separation of data and compute, right? The data is stored on S3 in open format. So you got to manage the data, of course, that never goes away, but you have to worry less about the compute, right? So I'll give you an example. We have, in our AWS edition, we automatically spin up the engines. So you can define different, what we call them engines, but you can define different engines for different groups within the company, the marketing group and maybe the executive dashboards that they have their own engine, and maybe that's a medium-sized engine and the other one's an extra large engine. But they're all running independently, and they all kind of spin up and spin down dynamically based on the workload. And so they're not interfering with each other. You're not having to deal with all this kind of fine-grained tuning of resources between these different workloads and worrying about, well, did the data science intern run a massive job that's going to impact the CEO's dashboard, right? So it's becoming a lot easier, and the amount of data engineering work or kind of operational work that has to go into managing these things is on the decline.
So is that because you have a higher throughput from the storage side so that you can just spin up compute resources as necessary, especially in the public cloud?
Well, I think it starts with the fact that you have somebody who's really willing to rent you servers by the second, right? And that's Amazon and Microsoft. Whereas on-prem, you basically bought servers and it took you 3 months to get the boxes from somebody like Dell or HP, and you had to rack and stack them. And so you didn't have much elasticity there, right? You couldn't just say, hey, I need 10 servers for the next 10 minutes for this workload, and then here, take it back. I don't want to pay for the other 23 hours and 50 minutes of the day, right? So it starts there, just having the ability to rent compute infrastructure. But then it also comes with the fact that you have that separate storage service that is accessible from all these different engines, right? So, even you look at a Dremio environment that has, multiple engines for different workloads, they all have access to that same S3 storage system and the ability to get kind of decent throughput there. But they also, when you look at some of the more sophisticated systems like Dremio, we also have built kind of caching technologies, right? So a Dremio engine doesn't have to go to S3 to get the same data again and again and again. We actually leverage the fact that Amazon EC2 instances have very fast SSDs or NVMEs on them, and we can leverage these NVMEs in a kind of a distributed way to cache the data locally close to the compute without the user even knowing that's happening, right? Because the NVMEs, they just come with a box. And so from the user standpoint, they're just getting faster IO than they'd get if we had to go to S3 every time. They're getting lower latency and also lower cost because you actually end up paying less for the S3 gets inputs.
So I want to start wrapping things up. And what are some big obstacles and challenges that you see in the whole data management space going forward?
So the challenges and opportunities for data lakes is really to continue to push the envelope in terms of kind of what's possible from a data management standpoint. And so historically, you kind of had a trade-off between data lakes and data warehouses as a company that was kind of building your data infrastructure. You could get the scalability, the low cost, the flexibility, the openness of a data lake, or you could get the kind of the all-in-one kind of functionality, the transactions, the data mutations, time travel that you get with a data warehouse. And that came at a very high cost and lack of flexibility and so forth. What's happening now in the world of data lakes is that companies like Dremio are basically taking that trade-off and eliminating that trade-off, right? Basically bringing the functionality of the data warehouse to the data lake. So that ability to have, transactions and record level mutations, DML, the ability to have time travel to query the data as it was yesterday at 9 a.m., all of that within the data lake so that you no longer have to move your data out of the data lake and into a data warehouse for any kind of use cases. And so I think if you look at fast forward, a year or two from now, basically data lakes will be solving all these use cases and there will be less and less of a need for a data warehouse out there. I think that's the big opportunity. And then you see things that are beyond that, of course, with some of the newer innovation, things like Project Nessie, which are providing that Git-like experience for the data lake. I think that also takes it kind of to that next level, enables things that really weren't possible before across any system.
Yeah, that's definitely very exciting. All right, so thank you so much for coming on the show, Tomer. This is Akshay Manchale for Software Engineering Radio.
Yeah, thank you. It's been great to be here.
Keeping your teams on top of the latest tech developments is a monumental challenge. Helping them get answers to urgent problems they face daily is even harder. That's why 66% of all Fortune 100 companies count on O'Reilly Online Learning. At O'Reilly, your teams will get live courses, tons of resources, interactive scenarios and sandboxes, and fast answers to their pressing questions. See what O'Reilly Online Learning can do for your teams. Visit O'Reilly.com for a demo.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.